This video serves as supplemental material for our submitted paper, Built Different: Tactile Perception to Overcome Cross-Embodiment Capability Differences in Collaborative Manipulation. To enable collaborative manipulation with tactile sensing across embodiments, we first train a policy using behavior cloning with demonstrations on a robot capable of impedance dynamics and with access to joint torque measurements. Next, we transfer the policy to a stiff robot without access to joint torques. The observation for this policy consists of a shear field representation derived from optical flow of a vision-based tactile sensor, the GelSlim. During demonstration, we use a 7-degree of freedom KUKA robot that is constrained to a planar workspace within which it exhibits malleable dynamics. We give an impedance controller parameters of low stiffness and high damping and continuously update the goal pose with some gravity compensation. When the robot is forced into a configuration by the human, pressing on the grasp box, it remains in that configuration. Forces, raw GelSlim images, and GelSlim shear fields and proprioception data are collected during demonstration. Training of the behavior cloned policy uses a DDPM to condition a noise prediction network on generative action output. We experiment with 3 modalities of observations as the input to this policy: shear fields as our main approach, and the end effector forces and the raw GelSlim images as our baselines. All 3 are fused with proprioception. Once the policies are trained, we are able to roll them out onto both the very same KUKA, only this time varying the dynamics of the arm, as well as our prismatic planar gantry bot, which only exhibits extremely stiff dynamics. Using the shear field-based policy, the KUKA is able to mimic the malleable behavior when using stiff dynamics with varying stiffnesses, allowing the human to conduct a box placement task while assisted by the robot. Unsurprisingly, the force feedback policy performs extremely similarly, exhibiting about the same distribution of effort/resistance on part of the human/robot. The raw GelSlim policy, on the other hand, performs poorly, exhibiting significantly more resistance toward the human's intention. GantryBot only has access to tactile information, and thus we are only able to compare the raw GelSlim policy with the shear field-based policy. As with the KUKA, the shear field-based policy allows GantryBot to mimic the malleable behavior that was seen during demonstration. This allows us to complete the same box placement task with assistance. The raw GelSlim policy performs just as poorly as with the KUKA, and the task was unable to be completed. Oftentimes, the human and robot would disagree, causing the box to be pulled from the grasp.